Welcome to The Explainer. Today, we're diving into a bit of a detective story. We're going to take a chapter straight out of geometry and treat it like an absolute masterclass in shape-shifting. We're looking at the concept of area, and I promise you, it is so much more fascinating than just memorizing a bunch of formulas. It's really about taking complex shapes, slicing them up in our minds, and transforming them into something incredibly simple. Okay, let's dive right in.
To start things off, let's tackle a trap that catches literally everyone at some point. Why do we count unit squares to measure area? I mean, couldn't we just use the perimeter, the length of the boundary to figure out how much space is inside? If a shape has a longer boundary, shouldn't it naturally hold more space? Well, keep that cognitive gap in your mind as we go, because the real answer completely shatters how we intuitively view physical space. So here is our roadmap for today. We'll start with the unit square foundation, explore the perimeter illusion, and then tackle triangles, parallelograms, and rhombuses. After that, we'll transform the trapezium and finally take all this into the real world.
All right, part 1, the unit square foundation. Think of area kind of like filling a beautiful shape evenly with Rangoli powder. We aren't dealing with some abstract floating theory here. We're simply figuring out how many non-overlapping unit squares, let's say 1 centimeter by 1 centimeter squares, can be perfectly packed into a specific region. At its absolute core, area is just a highly precise square counting exercise.
But counting every individual square? Yeah, that takes way too long. So we use a foundational shortcut. The area of a rectangle is simply its length multiplied by its width. If a rectangle is 7 centimeters long and 4 centimeters wide, it holds exactly 28 1 centimeter squares, 28 square centimeters. So the absolute crucial takeaway here is this. The rectangle is our ultimate truth. It's the master key. As we move forward, our entire goal is going to be turning every other shape in the universe back into a simple, reliable rectangle.
Moving on to part 2, the perimeter illusion.
Okay, so perimeter is the boundary, while area is the actual space inside. But here is where things get wild. Perimeter is actually not indicative of area at all. You can have a region with a massive perimeter that actually has a much smaller area than a really compact shape. Imagine a long, incredibly skinny rectangle. Its boundary goes on forever, but you can hardly fit any unit squares inside of it. The boundary's a total illusion. It simply does not dictate the space within.
Which brings us to part 3, triangles, or as I like to think of it, having the rectangle.
This specific puzzle is completely timeless. The ancient Shulbasuras from ancient India actually posed this exact challenge. Give a method to transform a rectangle into a triangle of equal area. They weren't just rote memorizing rules back then. They were physically dissecting shapes, trying to figure out how to fold a rectangle into a triangle of the exact same area. It's brilliant.
Think about it. If you take a rectangle and just slice a diagonal line straight across it, what happens? You divide it into 2 perfectly identical, congruent triangles. Because of that visual truth, the area of just one of those triangles has to be exactly half the area of the entire rectangle. And boom, there's our formula, 1/2 multiplied by the base multiplied by the height. We didn't invent a new mathematical rule. We just chopped our trusty foundation right in 2.
All right, part 4, parallelograms and rhombuses. Picture a slanted parallelogram. Now, imagine dropping a straight vertical line right down from the top corner. You've just sliced off a little right-angled triangle on one end. Now, pick up that sliced-off triangle, slide it all the way across to the other side, and stick it on. What are you left with? A perfect, straight-edged rectangle. You haven't added any area, and you haven't lost any. You quite literally just rearranged the furniture.
So because a parallelogram is just a rearranged rectangle, its area formula is exactly the same, base times height. No magic involved. And then we have the rhombus, which is a special type of parallelogram. If you slice it along its crossing diagonals, those perpendicular lines cut the rhombus into 4 equal triangles. Do the math on those, and it boils down to 1/2 times the product of those 2 diagonals. Once again, we derived everything simply by breaking it down into the familiar.
Next up, part 5, transforming the trapezoid. Now, a trapezium looks a bit intimidating at first, right? It's got 1 pair of parallel sides, but the rest is just totally uneven. Well, to turn that into a rectangle, we are going to use a simple duplication trick. Take your trapezium, imagine a perfect clone of it. Now take that clone, flip it 180 degrees completely upside down, and stick it right onto the slanted edge of your original shape. Suddenly, those 2 awkward shapes lock perfectly together to form one giant, beautiful parallelogram.
And we already know how to measure a parallelogram, right? It's just base times height. But wait, remember, the base of our new giant parallelogram is actually the top and bottom sides of our original trapezium added together. And because our giant parallelogram is made of 2 trapeziums, we obviously only want half of it. So, the formula for a single trapezium becomes 1/2 times the height times the sum of those 2 parallel sides. What looks like a complex formula is totally demystified just by cloning and flipping a shape.
Finally, part 6, measuring the real world.
Because look, we aren't just calculating area to pass a test. We use it to measure the physical space around us, from the tabletop you're working on right now to the floor plan of your entire house. And in the real world, we constantly cross between different units. Say you have exactly 1 square inch of table space, and you want to know how many square centimeters that is. You don't just multiply by 2.54, you have to square it. 1 square inch is precisely 6.4516 square centimeters. It's a tiny little detail, but it perfectly reminds us how unit squares actually scale physically.
So when we gather all these polygon formulas together, I want you to realize they are not just a random collection of disjointed rules you have to force yourself to memorize. They are a unified, logical family. Every single one of them, the triangle, the parallelogram, the rhombus, the trapezium, they are all just cleverly disguised rectangles. We've used mental folding, slicing, and duplicating to reveal that underlying truth. I really want to leave you with a provocative thought about scale. Once you actually grasp how to measure a tabletop, you essentially have the tools to measure the world. So think about this. Exactly how many times bigger is your entire city's area in square kilometers compared to the area of your school or your workplace? Really think about that. It's all just counting unit squares, just on a massive, massive scale. Try looking at your environment through this new mathematical lens today. Thank you so much for joining me on this explainer, and keep exploring.